So, anyone still up for a test, or everyone? Yeah, everybody's still happy.
Yeah, I think we're streaming already. So.
Oh, you're streaming already. Oh, okay.
Yeah.
So let me see. Oh, I think we have still half a minute. Maybe we just wait until some latecomers arrive.
Maybe you want to use the time to set up the first slides.
Yeah, and I should always I should double check. Is everybody of you fine, of the presenters, fine with recording this session?
Yes.
Yeah. Otherwise, please tell me, right? So that we would put you then to the end, so that we will stop the recording then whenever your presentation is up. Okay, everybody seems to be fine. Good. So I think we can start. So please, I guess, yeah, Mayam, you're, no, wait. Yeah, Mayam, you're the first one, right? So yeah. Please go ahead.
I'm going to share my screen. Cool. Can everyone see the slides?
Yep.
Great. So our paper is about information cascades in networks. In particular, we study asynchronous majority dynamics in some classes of trees. I'll just remind you of our model here and our results, and then we'll move on to questions. So our model is as follows. We have a graph, and each node is assigned a binary private belief or signal independently at random with a bias towards 1, where delta here is an absolute constant. And these private beliefs aren't known to the whole graph initially, but they're revealed to the graph through the following asynchronous process. Initially, no public announcements have been made, and then at each round, one node is chosen uniformly at random to make an announcement. And to do that, it will look at the neighbors that have announced and take the majority. And in case of a tie, it will announce its own signal. So a quick demo. We have the graph, nodes are assigned their binary signal. In this case, there's a bias towards red. Then one node is chosen uniformly at random. It will see that none of its neighbors have announced. There's a tie, it will announce its own signal blue. Similarly, no neighbor has announced. There's a tie, it will announce its own signal red. This node sees one blue neighbor, so it will copy blue. This node sees two blue neighbors, one red, copies blue. Finally, nodes can change their announcements. So this node sees one blue neighbor and this time announces blue. So in particular, there's one prior work that studies the same model as we do. And they show that in expanders with constant max degree, this process with high probability stabilizes in a correct consensus. And their work has two distinct parts. The first part uses sparsity to argue that in a slightly superlinear number of steps, most nodes have the correct announcement. And this is roughly because of the constant max degree assumption, most pairs of nodes are very far apart. And by a slightly superlinear number of steps, they're still independent. So we have a correct majority, a clear correct majority at this point. And then from this point on, they use expansiveness to show that once there's a clear correct majority, it spreads to the whole graph. Our result is we kind of relax both of those two assumptions in a sense. We show that this process stabilizes in a correct majority with high probability in two classes of trees, preferential attachment trees and balanced emery trees. And again, our proof has two parts similar to their work, where the first part is that a clear correct majority is reached after near linear steps. We show this in all trees. So in particular, they required a constant max degree assumption, but we show this for trees, which is kind of orthogonal in a sense. The second part is the fact that once this clear majority is reached, it will spread to the whole graph. And prior work used expansiveness, but because trees are inexpansive, we developed our own tools for showing this for two classes of trees. Yeah, so I'll leave it at
that. That's it? Yeah, you're done? Okay, great. Any questions?
Okay, so I posted one from Corinna Coppet. I think she's not here, but she forwarded it to me in case she's not. I posted in the chat. So do you want me to read it out, or would you want to read it out, or how's the procedure?
I can read it. So the question is, you assume that nodes are chosen uniformly at random, that each node picks the unweighted majority of its neighbors' announcements, and that graphs are acyclic. What happens if you relax either of these assumptions? For example, let announcement probabilities depend on node degrees, weigh nodes' announcements depending on node degrees, or allow for short cycles, for example, triangles. These are all really great questions. Some of them are easier to answer than others. I'll tell you what I think. So let's start with the uniformly random order. So if we let the order be proportional to the degree of the nodes, I think the process can fail. In particular, if you consider a star graph and then choose nodes to announce with probability proportional to their degree, the center is announced at every round with probability half, roughly. So with constant probability in the first round, the center announces, and again, with constant probability, it has the wrong opinion, and then all the leaves follow. So I think if you have a distribution where the probability of nodes being chosen is proportional to the degree, then the process could fail. I think if you have some form of inversely proportional to the degree or such, then I think that things improve, but I don't have any proof or evidence. But I will note that we can't hope for consensus, even if for any choice of distribution, just because think of the path graph, where roughly every node has the same degree. So the choice of like such thing, I mean, not any distribution, but anything depending on degrees. We show here in the talk that in path graphs, we can't hope for a consensus, but a correct majority is reached. And playing with order of announcements that is proportional to degree won't change things there. Well, there are more, I guess, drastically different orderings. There's also, like, on the other extreme, synchronous models, where in each round, every node announces. And those are generally better in that they reach a consensus always, and in more general classes of trees, graphs, they reach the correct consensus. Okay, so the next question was, if instead of taking the unweighted majority, we take some form of weighted majority, depending on the degree of the neighbors. I'm not too sure about this. My guess would be that it would be better because I guess like high degree nodes, especially like super high degree nodes, tend to be always correct every time they announce it could be correct. So if we weigh them higher, my guess is that it would be better. But again, we can't hope for consensus because of, again, the path graph. And then adding short cycle, that's a great question. It's kind of the direction in which we hope future work will take this. I think adding just one edge I've seen working fully for our classes of trees. But I guess we conjecture that if our graph has low arboricity, meaning its edge set is the union of a small number of trees, everything holds here. We haven't showed that. But especially if we can also assume expansiveness, we think that should be the case for even low arboricity. So yeah, we think like a small number of cycles won't affect the result negatively, but it's tricky to work with cycles just because the first part of our proof is mostly relying on independence early on. And like the moment you have cycles, you will have correlations from the very beginning, and that would just be tricky.
Other questions?
So there are none in Slack, so they might come from the audience if there's still time. But
can I ask a question?
Sure.
Yes.
Okay. My question is that how fast does this process reach the majority, reach the correct majority in this theorem 1?
Great question. So with high probability, I think in So I guess we have a bound that is the maximum of n log n steps and n times the diameter of the graph steps. So very quickly, fairly quickly, and the diameter, the intuition for the diameter is that basically for any pairs of nodes, the signal from one has to reach the other to be sure that there's no new change happening. And that's why we need to care about the diameter for like the signal to kind of move along that whole path.
So we have time for one more question. So you have results for balanced M-array trees and preferential attachment trees. How about arbitrary trees?
Great question. So we think hopefully it should hold for all trees, but it became tricky. So in particular, the second part of showing that the process stabilizes fast, we have some results that kind of characterize what kinds of trees this holds for, but it's not there yet. That's a great next work.
Yeah, the major obstacle, what is it? That the diameter could be too large and then it gets tricky?
Yeah, so the diameter could be too large. So the way our second part works, we show that by the time that this clear correct majority is there in part one, actually most of the graph is already stable and finalized. So nothing bad can happen. Like by the time where things can start being correlated and mess things up, most things won't change anymore. And that kind of uses directly the structure of these trees to show that like they have like maybe small subtrees that are low depth and they just stabilize within their own subtrees. So we have to look inside the trees a lot. So we needed extra assumptions.
Okay. Yeah, thanks. So we are done with the first presentation then. So then let's move on to the second. So please go ahead. Second is, yeah. Let me see, who is it? Ah, yeah, Nobu. Yeah, exactly.
Okay.
Yeah.
Can you see slide?
Yep.
Okay. Hello, I'm Nobutaka Shimizu, and this is a joint work with Takeharu Shiraga. And in this work, we consider voting process. In a voting process, we have a graph where each node have a binary opinion, and all nodes update their opinion according to a predefined some rule. And the aim of the process is to obtain the consensus. And this model has application in the consensus problem in the area of distributed computing. And for example, there are many models, and one famous example is the best of two. In best of two, each node picks up two random neighbors. And then the node computes a majority opinion among the node itself and the opinions of two random neighbors. So in this figure, the green node will be led in the next round. Another famous model is the best of three. In best of three, a node picks up three random neighbors, and the node computes a majority among the opinions of three random neighbors. Okay, and best of two and best of three or expander graphs have been studied so far. And their result says, roughly speaking, their result says that on expander graphs, best of two and best of three converge within log n rounds with hyperability if the initial opinion configuration has a bias. And in this work, we propose a general voting process. The name is quasi-majority functional voting, and this contains the best of two and the best of three. Then we generalize the previous known results. These previous results, and specifically, we prove that on dense expander graphs, quasi-majority functional voting converges within log n rounds with hyperability for any initial configuration. So we remove the assumption of initial bias. For example, from our result, we can say that L-Linear graph or a random regular graph with average degree larger than square root of n, then the quasi-multifunction voting converges within log n rounds with separability for any initial configuration. Thank you.
Thanks. So any questions?
So there was a question on Slack, which has already been answered on Slack, but I think I will still post it in the interest of the audience. Yeah, again, feel free to read out the question, or I can also do it if you prefer.
Sorry, I can't see. Okay. How much time do best of 2 and best of 3 or other natural process need to reach consensus in constant degree expanders? And just your belief for experimental result is good enough. If you have some arguments, that would be great. And thanks. And so our result says that on dense expander graphs, the best of 2 and best of 3 reaches consensus within log n steps. And the question in this question asks for the sparse constant degree expanders. And actually, this is a difficult problem for us, and we spent long time to solve this problem, but we couldn't answer yet. But in my numerical experience on random 3 regular graphs, the best of 3 reaches consensus within very quickly. So I think even if we have a constant degree expanders, best of 2 and best of 3 reaches consensus within at most polylog n rounds. But this is just my belief. Okay.
Further questions?
So none on Slack. So if there are any from the audience, please go ahead.
So I'm just wondering, what are the major analytical tools that you are making use of, like Markov chain theory or?
I see. The tool in this paper is expander mixing lemma. So, for example, so voting process can be seen as a Markov chain or a family of subset family of a graph, right? So, in this graph, there is a 2 to the n states in the Markov chain, but if we consider complete graph, then the state space becomes short. On complete graph, we can see the state becomes number of red vertices. And on expander graphs, we approximate. We use the same argument. So we approximate the Markov chain on 2 to the n states to the Markov chain on the 1 to the n states. And this approximation is a major tool in this paper.
I think probably once you go down to really low degrees, then the dependencies are getting so difficult to handle. You might have to, I guess, switch then to like witness structures or something like that. So I remember, for example, with these balls into bins games, right? People have used like witness trees or so to figure out.
Sorry?
And for balls into bins games, I remember people have used witness tree arguments, for example, because they had handled these dependencies, and it could be a guess how to proceed here as well, some kind of combinatorial witness structures. Because otherwise I would probably also see it as a very difficult task to generalize. I don't know, just a wild guess.
Thank you.
Any further comments, questions?
I have a small one. which may be a bit more technical. So if I recall correctly, that there's you have results for best of k, and the larger k gets, the faster stabilization occurs, right?
Yes.
So I was a bit surprised by this, because you didn't. This doesn't mean that the expander necessarily has a smaller diameter, right? So can you give some intuition as to why this works nonetheless?
I see. So my result about best of k. So in this slide, we introduce best of 2 and best of 3, and also so we can generalize best of k. And in best of k, the consensus time is log n over log k. So from this result, we can say that okay, our result on expander, our result of best of k on in my result, the condition is indeed strong. So in very dense expander, our result says that on a very dense expander graphs, best of k reaches consensus within log n over log k rounds.
Okay.
So, okay.
So they need to be dense, so the diameter will actually be smaller as well.
Yes, yes.
Okay, thanks.
Thanks for the question.
Yeah, so time for like one last question, if there is some. Okay, so then thanks for the presentation. And so let's move on to the next one.
Yeah. So I'll talk about next. So let me share my screen.
Right.
Yeah, so I guess you can see my screen.
Yep.
Okay, so yeah, so in this work, so the title of this work is New Extremal Bounds for Reachability and Strong Connectivity Preserver Under Failure, and this is a joint work with Kirti Choudhury. So in this work, our motivation is to basically study different graph theoretic problem under presence of network failures. So most specifically, what we study here is the construction of preserver. So what is a preserver? So preserver is a sparse subgraph such that it preserves certain property of the input graph. But the specialty here is that it should preserve even after some bounded number of failures. So in this talk, what I denote this number of failures by this term K. So for example, so if we take, say, connectivity property, so suppose this is a general setting where there is no network failure. So then what can be a preserver? So our preserver can be a simple spanner. And so if we store a spanner, so then it clearly preserves this connectivity property of the input graph. But the problem arises even if, say, suppose there can be one edge failure. So so you can now see that if you store this particular spanning tree, and now suppose this XY edge gets deleted at any point of time. So then now the graph is, so if you remove this X and Y, XY, this edge from this your input graph, then your graph is still connected. But when you have this spanning tree and you remove this XY, then this subgraph becomes disconnected. So, and this is the difficulty here. So that's why we want some type of subgraph such that even after one edge failure, so if the original graph is connected, we should get that that subgraph is also connected. Okay, so that is the main motivation here. So how can I construct such preservers so that it preserves certain properties under some presence of faulty edges? So in this talk, what we'll talk about two properties. One is strong connectivity and another one is pairwise reachability. So what is strong connectivity preserver here? So you have a graph G, so directed graph G and a parameter, and you want to construct a sparse subgraph H such that after any set of K failures, so so all the strong connectivity components of the input graphs and this subgraph should be same. So that means for any two vertices X and Y, in this G minus F, if there is an path from X to Y and Y to X, then there should be similarly a path from X to Y and Y to X in the graph H as well. So what we show in this paper is that if there are K failures, then we construct a subgraph which is of size K2 to the K and N to minus 1 over K. So you can now see that for small k, so this is a subquadratic bound on the subgraph that we show. And more specifically, if k is 1, so when it is single failure case, so then this is just a linear size subgraph. And now the second result is on the pairwise reachability. So in the pairwise reachability, again, you have a directed graph G and you want to construct a subgraph H, such that after this K failures, for any given pairs X and Y, so this pair set is also part of your input. So now for any pair, so if there is a path from X to Y in this G minus F, then there should be a path from X to Y in H minus F. Okay. So now what is known for this problem? So if there is no failure, so then there is a construction which keeps this n plus p root n and n p whole to the power 2/3 minimum of them. So basically saying that if there are root n many pairs, so then this subgraph will have only linear size. So for single source reachability, so there is a result which show that there is a subgraph of size 2 to the kn. So now the question is that in case of single failure for pairwise, so okay, so one should note that for the second result, so basically if you apply this second result for p pairs independently and take union, you get np size subgraph. So now here the main objective is to beat this np bound. So for how many pairs we can get some linear size preserver. And also like from if we go from single to dual, how this size of the preserver will change. So in this paper, what we show that we construct a subgraph H, which is of size n plus a minimum of p root n and n root p. So this is almost similar to case of non-failure, but there is a small difference here. So, but for root n pair, still we get a subgraph of size order n. And for any subquadratic many pairs, we get a size subquadratic. But for in case of dual failure, what we surprisingly show actually, so surprisingly we able to show that for there is a striking difference between single failure case and the dual failure case. So where in case of single failure for root n pairs, we can get a linear size subgraph. For dual failure, even for any n to the epsilon many pairs, we cannot get a linear size subgraph. We show a lower bound of n to the 1 plus epsilon. Yeah, so this is the polynomial gap between the single failure and dual failure case. And now this leaves us a few interesting questions. For multiple failure, whether we can extend our work or not, because all of our work is only hold for single failure. I mean, for the reachability preserver, not for the strong connectivity preserver. And also this gap between single failure and the no failure case. So the gap is only in this second term here. So where we get p root n and n root p. And but in case of non-failure, this minimum is over p root n and np whole to the 2/3. So whether we can match this bound for the single failure as well. And then for strong connectivity, whether we can get a linear size thing for constant k at least, because currently our bound is something like n to the 2 minus 1 over k. Okay, so that's all. Thank you.
Yeah, thanks. Any questions?
Okay, I can start again with 2 questions that have been posted on Slack. So here they are in the chat, and yeah, I hand over to the speaker again.
Yeah, so let me read the question first. So the two questions. One is, what is the motivation behind the strong connected preserver? And the second one is, are there any application for this failure tolerant preserver? So why, I mean, there are, one motivation is basically to, basically for any, so this failure, so this network failure is very common in practice. So say even like some network. So we want to find some kind of critical edge. So when we consider this reachability information between two vertices, we want to figure out that which of these edges are critical. So upon failure of which, whether this reachability information preserves or not. So that's why, so this is one of the motivation to identify such key players in this graph. And also, as far as I know, there is some application in computational biology, some kind of computation in steady state in some dynamic equation, but I am not completely sure about those applications. And then the second one, yeah, so are there any applications? So yeah, I already talked about this applications also. Yeah.
Yeah, further questions? So if it's very unlikely that two failures happen at the same time, you know, only one failure is happening at a single time, then of course one could ask the question, is it possible to repair the kind of the sparse subgraph quickly enough so that again you can handle another fault?
Yeah, so that is a very interesting question, but yeah, we have not looked into it so far.
Mm-hmm. Any further questions? Okay, so then thanks.
Okay.
Yeah. Oh, you have one, Christoph?
Yes, but it will also relate to a future paper. So maybe I can ask it then to both, or I can ask now, depending on the time.
Yeah, sure. You can ask now.
Okay, so do you have any intuition on what's going to happen for larger values of k? I mean, you have this lower bound that bounds it away from linear size, but do you think there's sort of a transition such that you can't really expect small preservers or reasonably small preservers may it even go up to near quadratic even for small sets of pairs? Or
So
what's your intuition?
Okay, so one intuition is that, I mean, why this some kind of transition happens from single to dual is that in case of single preserver, single failure preserver, there is a nice structure between any pair. So for any pair, so if you consider their paths, then you can see that there will be some kind of maximally disjoint paths. So there will be two paths and they will only intersect at the cut edges. But such structure doesn't preserve for dual failure preservers. So there can be actually even like order n many paths that you can embed there. So, and that is the main difference here. But what we expect is that, so our lower bound, so if you go back to our lower bound, so we show this n to the 1 plus epsilon over 8 for n to the epsilon many pairs. So, but for in case of single failure, we have actually two upper bounds basically. So p root n and n root p. So what we expect is that in case of general failure, this n root p, so this upper bound perhaps could be extended. but I guess that this P routine upper bound won't be extended. Yeah.
Okay. Yeah, so then thanks again. And so let's move on to the next presentation.
Okay, I will share my screen. Oh. Okay, can you see my screen?
Yep.
Okay. So let's begin. The title of our work is Node Connectivity, Terminal Backup, Separately-Capacitated Merge Flow, and Discrete Convexity. This is a joint work with Hiroshi Hirai. Our main problem is the node connectivity terminal backup problem, which is a special version of the survivable network design problem. We are given an undirected graph, undirected graph G with a specified terminal set with requirements. And then our goal is to find a minimum cost edge capacity function x. Oh. Does it work well? Oh, my screen
Yes.
has been blacked out. Oh, sorry. And our goal is to find a minimum cost edge capacity function x satisfying that for each terminal S, there exists a flow connecting S to other terminals capacity by X and node capacity C with value RS. We solved the fractional version of this problem, which is called the fractional NTB or FNTB, and give a first combinatorial polynomial time algorithm for FNTB. Our algorithm uses a connection between FNTB and a new kind of merge flow called separately capacitated merge flow. In this setting, unlike the ordinary node capacitated merge flow, each node capacity should be satisfied for each separated merge flows Fs. Which means connecting one fixed terminal S to other terminals. We show a max flow min-cut type theorem for this type merge flow, which extends Lovász-Cherkassky theorem to this separated capacity merge flow setting. Finally, let me briefly introduce our algorithm. Our algorithm is based on the combinatorial duality for FNTB. The dual problem is an optimization problem over subtree valued potential. Then this subtree space forms a median graph, a special graph class, which is a target of discrete convex analysis, which is a general framework for function minimization. And by combining this framework and cost scale, sensitivity and cost scaling method, we develop our algorithm. That's it. Thank you.
Yeah, thanks. Any questions?
Okay, let me start again. I post the question here. And yeah, please feel free to read it or make me to read it.
Okay. Oh, where is my chat?
I can just state it. So the question is whether you expect or guess that the NTB problem is NP hard, and if you think so, do you think there's a Peters, or is there rather going to be some gap and it's hard to approximate within some constant?
Thank you. For the first question, to be honest, I don't have any ideas to this problem, to this question. So first, let me explain the question. For for NTB problem, there is a 4/3 approximation algorithm by Fukunaga, and which is LP-based algorithm. And this is a special case of NTB, and this is not known whether the problem is P or NP hard. But I think but I don't have any reason for thinking that, but I think that the problem is NP hard because the Fukunaga's algorithm uses some like a stable set like approximation algorithm for stable set. So which is LP based and uses rounding technique. So I think NTB is more harder than stable set. So for the second question, there is a p-tas or it is hard to approximate within some constant. Yeah, to be honest, I don't have any ideas also for this question, but I hope that our method can be used to design an approximation algorithm which has a smaller approximation ratio than 4/3, because Fukunaga's algorithm uses some also uses special dual optimal solution, special structure of the optimal dual solution. So which is laminar biset family, and our subtree valued potential is also comes from the laminar biset family dual optimal solution. So I hope that this method, this perspection, which this combinatorial duality is, I hope this duality is useful for designing approximation algorithm.
Okay, thanks.
Okay. Thank you.
Further questions? So just to double check, for the terminal backup problem, these flows are concurrently for all terminals, or does the network just have to provide enough bandwidth so that every single terminal by itself could, let's say, satisfy its flow requirement? Just to double check so that I...
Yeah, there are, it is not required that concurrent there uses concurrent flow.
Okay, it's just for single flows, right? Like it should satisfy
yeah.
every single flow requirement somehow. Okay.
Yes, thank you.
Further questions? I'm just wondering, have you done any implementations of that? Would be interesting to kind of at least look at this and maybe some heuristics to see how well this would perform.
But I'm sorry for I didn't implement my algorithm.
Okay. Yeah, last chance for a question. Okay, so then thanks again.
Thank you.
And then let's move on to the next speaker.
Yes.
Again, yeah, it's to you, I guess.
I guess it's
right?
me. Yes, let me just share the screen. Just a second. Do you see it?
Yep.
Okay, perfect. So hi everybody. If you recall, this talk was about graph processes, like many of the previous talks do. In particular, something like a majority process where nodes switch to the most frequent color in their neighborhoods. For example, when you copy the opinion of your neighbors in a social network. And what we looked at is the proportional version of these processes, where, for example, you only switch if 70% of your neighbors have the opposite neighbor, or to phrase it otherwise, if 40% more people have, like based on your degree, 40% more portion of your degree have the opposite opinion than your current opinion. And also, a very similar topic is minority processes, where you want the least frequent color in your neighborhood. And that's a very similar setting, but we're going to focus on majority. And what we're interested in is the stabilization time of the processes here. We studied this in a sequential model and in the worst case. And unlike most of the work in the area, we were curious about what happens in general graphs. And our results show that the stabilization time in this case can be described by a strange non-elementary function that you see on the slide. And basically this describes a transition from a quadratic stabilization time to linear stabilization time as your switching threshold goes from 50% to 100%. And we can show an upper and lower bound for this up to a small epsilon in the exponent. And if you look at the formula, you might recall that the main parameter was this phi, which is kind of the part of the neighborhood that the node uses as outputs and inputs. So to maximize stabilization time, you would want to select phi portion of your outputs and only motivate these nodes to switch, and only be motivated by the rest of your neighbors to switch. So kind of in a directed fashion. And then one can show that in a level-based structure, the amount of increase in switches per level is described by this expression, and the number of levels you can have by this expression. And this kind of leads to this definition of f we have. And essentially picking this optimal value of phi corresponds to finding the best trade-off between this base parameter and the exponent parameter. So given that, since we can build a level-based construction with almost linear number of nodes on each level, this gives us this characterization, this behavior of n to the 1 plus f lambda steps, more or less, up to this small epsilon in the exponent. So yes, if you have any questions, I'm happy to answer them.
Yeah, so any questions?
Okay, I can start again with what's on Slack. So let me post the question and also read it. So the question is whether, so my understanding is that you have this result for 2 colors, right?
Yes.
So if you have more colors, do you think this will substantially change the game? So if you have many colors, even if there's a relative difference between them, this may still result in a smaller fraction of the node degree being affected, right?
Yeah, that's a very good question. So, in fact, when you look at the simple switching rule, when you switch anytime when you're above 50%, then it's usually quite easy to generalize to, well, at least to a constant number of colors. But this is indeed much more complex in this case. And the reason we didn't pursue this direction much is that once you go for more than 2 colors, then already these 2 definitions, which were equivalent in our case, these are not equivalent anymore. So the fact that you have 70% conflict on your edges, and that given, so the difference between the color you have and the color you're switching to is a specific threshold. So these definitions kind of diverge in this case. And then, of course, there's the question of which of them you follow. Also, I would think that this is the place where majority and minority also might be different already. So, for example, in majority, as for the lower bound, it also works with any number of colors, right? Because you can just take the same construction, and if the other opinions are just not present in this worst case graph, then of course they will never come into existence because nobody has any motivation to take them. So the majority lower bound also holds in this case, but for minority, of course, these non-existent colors will be a very promising alternative for nodes, and they will start appearing. So these are very good follow-up questions.
Yeah, so I was primarily thinking along the lines of the first definition, because that means there's substantial progress from a local perspective, right?
Right, yes.
But yeah.
Yeah, but I also agree to what you're saying. So even in case of majority and the upper bound, when you switch down to a given color, then of course it also matters how many neighbors you have of the other colors, because that determines how many conflicts you will have after this. So I would say that it probably requires some substantial changes to the upper bound.
Further questions? I have one question. So, one particular application could be social networks, opinion dynamics there. And of course, not everybody has the same threshold, right? Some might be easier, convincible, while others are harder to convince.
Right.
Any idea of what would happen in this case? I mean, is it possible to generalize your results in this direction so that you have different lambdas somehow for the participants?
Oh, that's another interesting question. So in some sense, this exact work that we're doing kind of avoids this question by looking at the very worst case. So even if you would have some limits on the lambdas that people could have, then probably a worst case, I'm assuming a worst case would only use the minimal or the maximal of these values. So I would say it would be very interesting to do experiments on this, but I currently don't see a specific theoretical question that we could attack in this domain. But since it's close to reality, it's probably worth thinking about it. I agree.
Any further questions? So you looked at what was it, the synchronous case, or?
No, this is sequential.
So, this is sequential, sorry.
So
would it change anything if you switch this one to a different model? Let's say parallel model.
Sorry, which model?
So the parallel, like they are working in parallel instead of sequential.
Yes. So I'm guessing that the stabilization time would probably be significant. So the worst case stabilization time would probably be smaller in case of the synchronous case. So this lower bound example we have for the whole lower bound behavior is heavily dependent on this careful timing of nodes, where the upper nodes, so nodes with higher degree kind of switch smaller number of times, and they kind of wait for the lower degree nodes to do the switching that is required to reach this maximum. So in that sense, this is maybe not a very realistic model of a practical opinion dynamics. In some sense, on the other hand, the synchronous case has this problem that it can have neighbors switching at the same time and maybe infinitely going behavior, or like these periodic cycles. So we were kind of always interested in what's a realistic model between the sequential and the synchronous case, because in some sense, both of them are not a perfect model of reality, but we still haven't found or perfect candidate for that, to be honest.
Okay. So, chance for a very last question. Yep, then thanks again.
Okay, thank you.
And we'll move to the last presentation of today, for this session, I mean.
One second. Okay, so just a quick reminder of our work. So it is a joint work with Greg Bodwin, Kirti Chudhari, and Mara Farter. And our work is about new fault-tolerant subset distance preservers. So a quick reminder of what it is we're handling the question of given a graph G and a subset of sources S. We want to preserve distances by creating a sparse subgraph that keeps all the distances between the pair nodes of S. And we want it to handle failures, which means that even in the presence of a failure, all the distances between the yellow nodes, which is our subset S, remains the same between G and H. Or formally, you can see it here, that the distance remains the same in the presence of any fault. And in this work, the faults are vertices, but the definition holds also for edges, as we saw in the session before. So our results are as follows. So we present bounds that match the state-of-the-art bound for edges. That is for any n-node undirected weighted graph G and subset of source nodes S. We show that we have a subset vertex fault-tolerant preservers with n tilde of ns edges, and this match the state-of-the-art results for edges. And also we show that when we have only one single pair, and the bound is linear, and this also matches the state-of-the-art results for edge faults. And we also show a lower bound, and this applies for weighted graphs only, and that is that we need at least ns edges for any subset of source nodes S and any n. So we show a weighted graph that needs at least this many edges. But we also mentioned that we note that for subset distance preserver, for subset distance preserver in the fault-free setting, current bounds show that the state-of-the-art upper bound is O of ns, and we show a bound that is very close, and we conjecture that if this bound is, if we don't improve in the fault-free setting, so we conjecture that this lower bound holds also in unweighted undirected graphs. And we also have results for directed graphs. In the directed graph, the only solved setting was for one single pair, S and D, and for edge faults. And we show the following results. We complete the picture for directed and unweighted graph. And the following settings are a graph G and a set of source nodes S and a designated root R. And we look at the case where the pairs that we want to preserve distance between are all the pair nodes of R cross S, which means all the distances between R and this set of source nodes S. So we show that there is a fault-tolerant preservers with O tilde of n to the 4/3, S to the 5/6 edges. And when S is equal to 1, which means that again we deal with one single pair, this bound improved to be O of n to the 4/3. And this result also has a conditional lower bound. And finally, for the directed and weighted graph, we extend the previous results. And for the same setting, we show that there is a fault-tolerant preserver with O tilde of n to the 3/2, S to the 3/4 edges. And just want to talk about two simplifications that we made in our technique that I think that can be useful to other works as well. So first, we analyzed only short replacement path, and this is due to a heating set argument. We just sampled another set of random S nodes, and then we made the analysis again. So we could assume that all replacement paths that remains to deal with are short, relatively short. And the second thing is that we analyzed failures only on a single path on the shortest path tree. So imagine that this triangle is the shortest path tree rooted at this top node at S. And this green path is one path of the heavy path decomposition that we used. And what we did here was to analyze failures only on a single path and with respect to the subtree rooted by the top of the path. And this way we could analyze locally the failures and just assume that they're just failures on a single path. And using the heavy path decomposition, we could unite it and not create a bigger graph. We just we can unite it and see, and because of the property of heavy path decomposition, we could just create a sparse subgraph. So that's it.
Thanks. Questions?
Okay, yeah, there are a couple. So let me post them. They're all a bit different. So the first one is, as I mentioned earlier, it's very similar because it's very related settings. So the question is again whether you think that for two or more faults, there's hope for getting subquadratic preservers if S is small enough.
So I think that there is a result about that in some other setting. I don't know, but my intuition is that in two faults it can become quite large. In other settings we saw it, so that's what I think, but I'm not sure.
Basically, once we have already a single source with respect to everyone, we can have subquadratic subgraphs as long as F is sublogarithmic, is sublog n. This is the upper bound that we have even for S cross V.
Okay, thanks.
Then, Christoph, you want to go to the next question?
Yes, so let me proceed to the second one. So yeah, have you thought about trying to get competitive solutions instead? So depending on whether the graph admits a smaller preserver, whether you can get close to that.
Yeah, you mean optimization algorithm. Yeah.
Yeah.
Mm-hmm.
So we thought of.
Yeah, go ahead, Noah.
No, so we thought about the approximation approach, but we couldn't find something that is worth to add to this paper. We had a result of it is NP hard to approximate the subset fault tolerant preserver in the unweighted undirected graph. But we couldn't find some approximation. It is only hard. We only show that it is NP hard to approximate.
Okay.
Within a log n factor.
Yeah. Okay. And the final question was just, I think, a minor confusion on my side. You had this lower bound of n to the 3/4, I think.
Yeah, I'll go to the presentation.
And
yeah,
I was just wondering, isn't it trivially linear size simply because, you know, if your graph happens to be a path, you just, regardless of faults, you just may have to take all of that to preserve connectivity between the endpoints.
The lower bound in the single pair case is
Yeah.
trivial, but the upper bound is the one that is not trivial here. Well,
yeah, I mean,
I'm sorry, maybe I misunderstood.
There was another slide where you had this.
Co-weighted graphs.
Yeah, yeah, that one. So I was confused about this omega n to the 3/4 because shouldn't it be linear automatically?
It's 4/3, I think.
Oh yeah, it's 4/3.
Ah, okay. That makes more sense.
Sorry. no, it's 4/3. I'm sorry.
Right. Further questions? So I guess one question that I already asked in the previous talk, if there is a fault, yeah, and so therefore you also need to adapt then your structure to again be able to handle a single fault. Do you happen to know how difficult it is? Have you looked at this? Like, is it easy to adapt your given distance preserver to a new one?
You mean I'm sorry, I'm not sure that I understood. You mean that I have some graph and then you want to edit this graph, say delete one vertex, and then you ask me about the new subset fault tolerant preserver?
Yeah, because you again want to be able
like
to
dynamic graphs.
Yeah. Like you again want to be able to handle a fault, right? So you therefore need to kind of recompute, right? In the worst case, you would just have to recompute from scratch. And I'm kind of wondering whether, you know, I mean, it looks like you should be able to preserve a lot, yeah, in preserver, hopefully. I'm not sure, right? So
yeah.
I don't know whether you have ever looked at this.
Yeah, so I'm not sure as well, but actually our proof is a mathematical, and the algorithm is just to take all the shortest path that there is in this graph that are path between two target nodes, and the replacement path is over one failing node that is on the shortest path. So because we take exact shortest path, we can just try to compute if we made a change to the graph, say deleted the vertex, so we can think of how does it affect our count or try to find all the replacement paths that this vertex is in. And I think that there are a lot of works about trying to check this. I mean, trying to check if a vertex appears on a replacement path. So I think that would be the direction that I would go to, but we didn't explore this question.
Yeah, it looks like it's going to be hard to maintain it dynamically. I mean, I think there are simpler problems for which we don't really know how to solve. And the construction, as Noah said, is very global. It's not like a local kind of argument. Wow. So really, it is just take all the replacement paths that you need by the definition, and then we just need to do some counting argument to show that the collection of edges that you take is small, because there are many overlaps between the replacement path. So the cleverness is more in the analysis rather than in the algorithm itself, which is basically what you need in order to have dynamic algorithm. You need a completely different approach to take.
So I guess if the diameter then is small, maybe, or yeah, well, probably also things have to spread quite nicely, so that hopefully then also in the algorithm there wouldn't be much of a change if you take away an edge and you do the recomputation.
Yeah, I mean, if the diameter is small, also the bound can be better. So usually these bounds are interesting, especially when the diameter is large.
Okay, any further questions? Great, so we are done with this session. So thanks again for all of the speakers, and hopefully you will enjoy the rest of the conference. And as usual, if there are any further questions that we didn't weren't answered here in this session, please post them at Slack so that the authors can address them. That's it. I think we can now stop the recording.